Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today I'm going to be giving you an introduction to random variables. So let's talk a little bit about what a random variable might be. What is a random variable? Sometimes I will use this notation. Just a capital RV, meaning random variable. All right, very simply, a random variable is a function. It's a function in the usual sense. It's a function that maps outcomes of a chance experiment to real numbers. A random variable is a function that maps the outcomes of a chance experiment to real numbers. Random variables are what I commonly say user-defined. Random variables are user-defined. You get to pick the random variable in many cases. You get to define how real numbers are assigned to outcomes of chance experiments, but the definitions, random variable definitions, ought to make sense. Random variable definitions ought to make sense and should be chosen so that we can use our mathematical tools to understand the random nature and the probability of outcomes for various chance experiments. So it should be chosen so as to allow the use of mathematics to understand the randomness of our chance experiment and the probabilities of various outcomes and events. All right. So, what's our typical notation? Our typical notation for a random variable looks something like this. Okay. This little x is the real number. That's a real number. Alpha, remember a lowercase Greek letter, is what I'm going to use to denote an outcome. And my random variable random variable function is going to be denoted by a capital English letter in most cases. In this case, I drew bars above and below a large X to indicate that that's the capital letter. Some textbooks use boldface lettering. I've seen some use over arrows and things like that. I'll do my best to distinguish between the lowercase real number values and the capital random variable assignments. So random variable function will somehow be denoted by a capital letter. All right. A couple of things to note before we move on. And do some examples. Is after an experiment is performed, my random variable takes on specific values for each outcome. After an experiment, chance experiment E, is performed, the random variable takes on After chance experiment is performed, X takes on a specific value for each outcome, alpha. However, before the experiment is performed, the probability that the random variable takes on a specific value is determined by, or is influenced by, it's influenced by the probability of the various outcomes. All right, so what I'm trying to get at here is that the randomness in the chance experiment leads to certain probabilities of the various outcomes. The randomness in the chance experiment then translates, in effect, through the random variable assignment in such a way as to give rise to probabilities that the random variable itself takes on specific values. So we can talk about chance experiments, or we can talk about random variable assignments, and if we make our random variable assignments cleverly, we can look at probabilities of random variables taking on specific values and directly get at the probability of various outcomes and events of my chance experiment. Okay. One further note before I move on is, once again, my random variable assignment is a function, so more than one outcome in the sample space for my chance experiment can be mapped to the same real number. All right? This is the same as for any function. So, for example, this is not a random variable example, but for example, if my function is x squared, we know that this is a function in the usual sense. Well, f of minus 2 equals f of plus 2 equals 4. I can have multiple inputs that yield a common output. All right? So just keep that in mind. We need to be clever about assigning defining our random variables. Because multiple outcomes can give rise to the same real number assignment, in some cases, our random variable assignment may or may not help us. And we'll see that in an example in just a few minutes. All right. Let's do an example. My chance experiment is toss 2 fair 6-sided dice and observe the number of spots up. Alright, I'm going to toss 2 fair 6-sided dice and observe the number of spots up on each die. The sample space is going to have 36 equally likely outcomes. Equally likely outcomes. And I'm going to denote my outcomes this way. Alpha sub I j. This is an outcome. And little I indicates number of spots up on die 1. And j is number spots up on die 2. And let's pretend that my dice are somehow distinguishable from one another. One's red and one's green, one's large, one's small. Somehow you can keep track of which die is which. All right, let's talk about some possible random variable assignments. All right. Could be one of multiple different things. I could maybe multiply I times j. It's simple enough to do. I could multiply the spots together. Or maybe I might want to divide I by j. That would give me a real number. Or maybe I could take the spots on the first die and raise it to the jth power. I could do that. Or, I don't know, something crazy. I could do the square root of I times j raised to the 23rd power. I could do that. I don't know why on earth I'd want to do that, but I could do that. In all cases, I end up with a real number. I take an observed outcome, and I do something with my observation and assign a real number. Each of these are real numbers. That's supposed to be yields. Each random variable assignment here yields a real number, but the question is, are they useful? That's up to you to decide. Are the random variable assignments useful to you? All right. Well, we've all played board games before. We're still considering my toss 2 dice and observe the spots up experiment. The most common random variable most common random variable for tossing 2 fair dice and observing the number of spots up is to simply add the spots. Okay, so this is the random variable that we're going to play with for the rest of the day. Just add the spots. Okay, that's all we're going to do. All right. So, for example, x sub alpha 5, 1 is going to equal x of alpha 4, 2 equals x of alpha 3, 3 equals equals x of 2, 4, whoops, alpha 2, 4, alpha 2, 4, which equals x of alpha 1, 5, and of course these all equal 6. 6 spots up. All right? In other words, if I have 5 spots up on the first die and 1 spot up on the second die, or 4 spots up on the first die, 2 spots up on the second die, etc., 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 I end up with 6 total spots up. All right? In this particular case, there are 1, 2, 3, 4, 5 possible outcomes out of the 36 that yield 6 spots up. All right? 5 possible. Five possible outcomes of the 36 that yield a random variable value of 6 total spots. Okay? All right. This is the random variable assignment for our current experiment. This is the values of the random variable assignment that's equal to the sum of the spots up when 2 fair 6-sided dice are tossed. And we'll see that there's 1, 2, 3, 4, 5 ways that I can get 6 spots up, etc., etc., etc. Okay? All right. Let's look at how we can continue with the same example. Continue with the same example, tossing 2 fair dice, and I'm observing the 2 spots up. Or excuse me, I'm observing the spots that are up on each of the 2 dice, and my random variable assignment is to add the spots. All right. That's my random variable assignment in this particular case, just add spots. All right. And let's calculate the probability of some events. 1. Let's let event A1 be this. All right, remember that an event is a collection of possible outcomes. This event is the event that there are 6 total spots up. Okay, the probability of A1 is clearly 6/36. All right. Going back to my random variable assignment table, there are 1, 2, 3, 4, 5. Oops, I made a mistake. This is 5/36. 5/36. There are 5 possible ways of getting 6 total spots up when I toss 2 fair 6-sided dice. My apologies. Okay? Let's look at another event. Event A2 equals alpha 1, 2, alpha 2, 1, alpha 5, 6, and alpha 6, 5. This event is the event that the This is the event that the total number of spots up is equal to either 3 or 11. All right? Okay. Looking back over here, I have 2 ways of having 3s, and I have 2 ways of having 11. All right, in my event, A2 over here includes all possible ways of getting a 3 or getting 11. I didn't leave anything out. So this event is the event that the total number of spots up is equal to either 3 or 11. Clearly, there are 4 check marks on the screen right now. There are 4 possible equally likely outcomes in this event. My probability of A2 equals 4/36. Okay? All right. What about this event, though? Let's define event A3 this way. Alpha 3, 1, alpha 4, 3, and alpha 5, 4. How would we describe that in words? This is not equal to the event that the sum of spots up This is not the event that the sum of spots up is either 4 or 7 or 9. Why is that? All right. Alpha 3, 1 is that guy. Alpha 4, 3 is that guy. Alpha 5, 4 is that guy. But there are additional ways by which I can get a 4. There are clearly multiple ways by which I can get a 7. And there are several ways by which I can get a 9. My event E3 does not completely exhaust all of the possible ways of getting a 4 or a 7 or a 9. Okay? It simply doesn't. I do, however, have three outcomes in this event, and they're equally likely. There are 3 of the equally likely 36 outcomes in my sample space. It's true that I can write down that the probability of A3 equals 336, but this is not equal to the probability that x, my random variable, which is the sum of spots up, it's not equal to the probability that x equals 4 plus probability that x equals 7 plus the probability that x equals 9. Going back here, there are 3 ways that I can get a 4, there are 6 ways that I can get a 7, and 4 ways that I can get a 9. The right-hand side of this inequality is actually equal to 336 plus 6, 36 plus 4, 36, all told it's 1336. Clearly 1336 is not equal to 336. So what I'm getting at here is that this particular random variable assignment, being that we add the total number of spots up, did not help us in this case for finding the probability of event A3. It helped us in the other 2 pieces, but it didn't help us here. The point I'm trying to get at is that you need to consider what you want to get access to when making random variable assignments, and you need to make your random variable assignments cleverly so that you can get the most use out of them. All right. Let's talk now about some probability distribution functions, some ways of quantifying and describing the probability that random variables take on certain values. So, probability distribution functions. Probability distribution functions. These are ways of describing the probability that some random variable some random variable x takes on specific values, denoted by little x. There's 3 different probability distribution functions that we're going to concern ourselves with. I'm going to write them down, then I'm going to show you what one of them looks like, and I'll pick up with the other 2 in the next video. The first is what's called a probability mass distribution. A probability mass distribution, sometimes I will denote this by a capital P M D, probability mass distribution. Probability mass distributions are best for when we consider discrete random variables. By discrete, I mean that the random variable takes on only a specific set of discrete values. Random variables can be discrete or continuous. I can have a finite number of real numbers assigned to my random variable, as in the case of toss 2 dice and add the spots up. In the toss 2 dice and add the spots up example, my random variables, the random variable assignments are discrete. It's 2 through 12, and it's finite. I can't be less than 2, I can't be greater than 12. I can have infinite number of values excuse me, assigned to my random variable. I can have a finite range of values for my random variable. They can be discrete and they can be continuous. Probability mass distributions are best for discrete random variables, and they're very simply a table or plot of the probability that X takes on each real number value little x. Probability mass distributions are usually either tables or plots of the probability that my random variable takes on each possible real number value little x. All right. The second probability distribution function that we will encounter is called the cumulative distribution function. Cumulative distribution function. I will sometimes denote this as a CDF. And this will be my notation. A capital English letter subscripted by my random variable, evaluated at the real number value that the random variable takes on. This is the probability that my random variable is less than or equal to some real number value. Okay? Especially in the case of discrete random variables, this less than or equal sign is going to be very important. We can be a little bit sloppy when we start talking about continuous random variables, but for discrete random variables, that less than or equal sign is going to be very, very, very important. All right, the third distribution function that we need to know about is going to be called the probability density function. This is denoted by PDF. And this one is a lowercase letter subscripted by my random variable designation as a function of my real value assignments. And this is simply the first derivative of my cumulative distribution function. All right, we will look at the cumulative distribution function and the probability density function in the next video. We'll look at the properties and do some examples. But for now, I want to go back to our earlier toss 2 dice experiment and talk about its probability mass distribution. So, we're going to reconsider the prior example, toss 2 fair dice, 2 fair 6-sided. Toss 2 fair 6-sided dice. I'm going to add the spots up. And my random variable assignment is that. All right. I'm going to add the number of spots up. Remember that this is my table demonstrating my random variable assignment. Let's erase some of these marks off of here. All right. Well, very clearly, there are two ways of getting a 3. The probability that x equals 3 is 2/36. All right? The probability that random variable is 5 is what? 4/36. Probability that my random variable is 11. Probability that my random variable takes on a value of 11 is 2/36. The probability that my random variable takes on a value of 12 is 1/36. Way down there. Okay, so I could calculate by just observation of this table the probability that my random variable takes on values from 2 through 12. And plot them. That's my result. All right. There are exactly one way out of 36 to get 2 spots up. There's exactly 3 ways of getting 4 spots up. There's exactly 1 way of getting 12 spots up. You'll notice that it is impossible to get 13 spots, 14 spots, 15 spots, 1 spot. I can't toss 2 fair dice and get 1 total spot up. I can't get 0 either. So this, and by the way, you'll notice that on the vertical scale, my probability is multiplied by 36. All right. So this, if I divide by 36, that's actually 1/36 probability. This is 6/36, or 1/6 probability. Okay? Don't forget that. All right, so this is simply a plot of the probability for my toss 2 fair dice and add the spots up random variable assignment. It's as simple as that. Okay? Well, that's all I've got for you today. As always, if you have any questions, please feel free to contact me at your earliest convenience, and I'll do my best to answer them as thoroughly as possible. Have a nice day.